Hi, my name is Paddy Delaney from Huber, and today I would like to discuss chiller technologies for laboratory distillations. At Huber, we've got a long history of producing environmentally friendly refrigeration systems that are used quite widely in research and development, in particular in R&D labs. Part of work in R&D labs is often around solvents and using them in synthetic chemistry, analytical chemistry, or crystallography. And at some point, these solvents have to be removed. There are many traditional ways of distilling solvents, but what we would like to do is show you how to do it safely, accurately, and reproducible, so that we increase your solvent recovery and increase the safety in the laboratory. When we look at a distillation, there's an energy balance here. And some people look at it like a triangle. For distillations, you apply heat to your distillate, and you also apply vacuum to reduce the boiling point. So you can reduce your boiling point, therefore, in theory, be able to distill at a lower temperature. So applying heat and vacuum are outside of the Huber remit for distillations, but the key critical component is the condensation. And we believe this is the most valuable parameter to play with. If we think of your standard rotary evaporator, we have heating in the round bottom flask, and you can see in the vapor duct here, this thermal imaging, we're going up and the vacuum is reducing the boiling point, and we're catching our condensate in the bottom, but you will see the cooling coil a darker shade because it's run colder. When it comes to laboratory distillations, one of the key factors to calculate is the required cooling capacity. This is basically done on the weight of your solvent, the heat of vaporization of your solvent, and the time that you want to distill off that solvent in. Bearing in mind you want to do it safely so you don't have bumping of your solvent and the material you're leaving behind in your distillate flask. So to do this, let's first just draw out the application, because it's often just so we understand where things are coming from. So in a rotary evaporator, you have a heater bath that's typically 2 to 3 kilowatts of heat. We have a motor which rotates our flask, which holds our mother liquor. We then go up to our condenser, which commonly people have been using single pass water on it, but more and more people are going for chiller technology. So this would be where our Huber is connected into it. The gas will obviously condense, fall into our collection flask, and then further across here we'd have our vacuum. If we think back to our little triangle here of energy balance, key factors here are heat, which is normally fixed. So in this case for ethanol, we'll do an example. We'll say 30 degrees C. Our vacuum is at 70 millibar, and they're fixed constants. So to ensure that we get recovery of solvent, the key factor here is what cooling power is required to ensure maximum recovery. So in this case, we're going to propose we're distilling 1.5 litres of ethanol. Next key fact is we want to do it in 1 hour. We need to know the specific heat of vaporization of ethanol, which is 841 joules per gram. So if we do a wee quick conversion here, that is essentially 841 watts seconds per gram. And we also do ethanol, so we want to go back to grams. So density of ethanol is roughly 1, so we'll be able to say 1500 grams. And while we're at it, 1 hour is 3600 seconds. So we've got all of our base units converted to the kind of standard SI. So what do we need to look at? So to calculate the required cooling capacity, we've got the heat of vaporization times the distillation rate divided by the time, basically. So in our case here, we've got 841 watts seconds multiplied by 1,500 grams times the time. So in this case, we can put in the hour symbol here because we can easily remove that in a second. And that is over 1 gram by 1 hour by 3,600 seconds. So what we can do now is we can knock out some variables. So we've got hours cross hours, grams with grams, watt seconds with watts. So as you can see, we're now left with watts in our equation, which would be the cooling power. So in this case here, we're left with, to distill 1.5 litres of ethanol in 1 hour, we'd roughly require 350 watts of cooling power. And this is quite a simple equation that we can put across. Obviously, if you've got mixtures of solvents, it's a little bit more tricky, but you can work it. So if we look at our common laboratory solvents and apply the same 1.5 litre per hour, but keeping the water bath at 30 degrees C, we can see with water we'd need nearly 900 watts because it's very high specific heat capacity. It doesn't transfer heat that well. But the more common solvents like toluene, ethanol, IPA, isopropanol, hexane, acetone, and even dichloromethane and diethyl ether, which are very low boiling solvents, we can see how much cooling power we need to apply. So, how do we size a recirculating chiller then for your rotary evaporator? Well, from my days back in the medchem labs and the process chemistry labs, we used to divide solvents into two groups. The easy to distill ones, so group A, such as toluene, hexane, ether, dichloromethane, and the ones which would bump or can hold some water and therefore are a little bit more sluggish to distill. So we'd have your alcohols basically. So when we bear these groups in mind and we consider standard flask sizes used in teaching labs could be anywhere from 50 ml up to 250 ml. If you go to your medchem lab, they're working up to 1 litre maximum, but you could go to a process chemistry lab which are using up to 20 litres. And using our kind of heat of vaporization calculation to convert it into required cooling power, we can devise this table here. So we can say that we can look at which Huber product is required to apply the correct cooling power for that application. These range from the smallest, the mini chillers, the 280, the 300 and 600, up to about 2 litres. Once you go above that to a 3 litre distillation flask, which is more of a small process rotary evaporator, all the way to your larger 20 and 10 litre rotary evaporators, we can see that we might need 1 kilowatt of cooling, 1.2, 1.5 kilowatts of cooling, and for the very big ones, about 2.5 kilowatts of cooling. These numbers we have also verified in the lab and shown that you can use these solvents and these combinations and ensure that you get high recovery of solvents. We will go through recovery of solvent rates slightly later on in this presentation. A common question often posed to Huber is, can I use one chiller for multiple rotary evaporators? And the answer is, of course you can, but the application is king. So you need to look at the required cooling power for your application. We then have this nice table where we've devised, starting from our little baby mini chillers all the way to the Unichiller 15, how many rotary evaporators you can connect onto your system. We often go into laboratories and are quite shocked about the setups people see in on their chillers. Quite often, people hook up chillers in an unbalanced fashion, or, as is also known, in series. And we can see here, whilst the cooling power is delivered to rotary evaporator A, the output has warmed up because it's removing heat from the application. You're then getting warm thermal fluid into rotary evaporator B, which then heats it again, and by the time you get to rotary evaporator C, you've got very little cooling power, if any. And you will notice that you will get condensation does not occur on the coils in rotary evaporator C. And at this point, you're probably best off checking the trap on your vacuum pump, because it will most likely contain solvent. If we try to do a balanced system, where we pump out from the chiller, and we go to a split manifold, such as the Huber pentagons or octagons, we can then get an equal balance, so each rotary evaporator gets thermal fluid in at the same temperature. And they will return thermal fluid out at roughly the same temperature depending on the application. Obviously, if you have 3 identical loads, you'll get identical outputs. But in this case, you could have different solvents on each rotary evaporator. When choosing to run a balanced application, it is key to ensure you have a manifold where you could take an application offline but not affect the others. This is why using dry brakes, such as the CPC ones here, is quite a valuable tool, reducing downtime. So we've talked about calculating our power loads, how many rotary evaporators I can connect to one chiller, how do I set them up on one chiller. But what we've kind of glossed over, and a key point, is by connecting a chiller to your system, you are then reducing single pass water. Single pass water is one of the most expensive utilities for universities globally. And what we've done here is, through a survey of UK universities, we've looked at how much water they've been using per tap. And we've based this on 210 days of a year and 8 hours per day. And what we can see from a survey we carried out on, I think it was about 25 universities, we get a range of 2 litres a minute all the way up to 20 litres a minute. We're quite often asked, Paddy, how much money can we save if we stop using water in the lab? The trouble is we don't know, because we don't know how much water you use in the lab. So what we've done here is taken average UK prices, and we can find out for different countries the cost of water in and water out. And then by using this graph, we can plot roughly where you'll be. But the key thing to remember here is this is one tap getting removed on one application. If you decide to connect multiple rotary evaporators to one chiller, you may be taking out 2, 3, 4 taps. Therefore, instantly saving your water usage of a wider range than if you had one application. People often ask, your chillers have an operational range of -20 to 40 degrees. What is the best temperature to set the chiller at for distillations? Well, it's quite simple. If you look at the cooling power of the unit, you'll notice that 15 degrees to 0 degrees C, it's got the maximum cooling power it can apply. So one of the key factors here is how volatile are the solvents and the chemicals you're trying to distill. If you work in the flavorings or aroma industry, you might want to set it at -10, because you know that you'll catch those low boilers there. But for most people, running between 15 and 10 degrees C is fine. A couple of reasons for this. If you're in a laboratory that's quite humid, you might find that you're getting condensation on your pipework if you go below 10 degrees C. If you're running just water in there as your thermal fluid, going close to 5 to 4 degrees, you'll start building up ice because it will start to propagate on the evaporator. So kind of the golden point is 15 to 10 degrees C. We can go colder if the application needs it, but again, the application is king. And this is where we're running on that. So on the table here, you'll see our mini chiller 280 has 280 watts at 15 degrees. And at 0 degrees, you've got 200 watts. So there's plenty of cooling power at the lower temperatures. All the way, you'll notice this trend all the way through the Huber product range. We've designed a multi-purpose chiller that delivers high cooling power at low temperatures. So whilst we have discussed at what temperature should we run our systems, we're quite often asked, what thermal fluid should we use in there? A lot of chiller manufacturers tell people just put water in your chiller, but you have a couple of issues here. A, you can't go below 4 degrees C, and B, after about a month or so, you might see you've got algae growing in your pipework. That little bit of green that appears on transparent pipework and in the glassware. At Huber, we suggest people use monoethylene glycol, and there's a couple of reasons for this. By adding glycol to water, you improve the specific heat capacity of that thermal fluid. By adding different ratios of glycol to water, you can achieve lower freezing points for your thermal fluid. So quite a common one we tell people to run is either a 40-60 mix or a 50-50 mix of glycol water, which will cover your mini chiller 280 all the way down to your uni chillers that operate at -20. Another option people use is ethanol water mixes or IPA water mixtures, but this is often site specific. At the beginning of this webinar, I mentioned how Huber have been involved in the R&D section of the chemical industry for quite a long time. One of our first inventions was the Huber rotostat back in the 80s, working hand in hand with distilleries and chemists. We designed our own distillation equipment where we have a heating bath. Just like a rotary evaporator, it's agitated by rotation. We have a cooling coil to catch the gases and condense them. However, in this case, the secondary distillation was prevented via cooling coil on the condensation trap. And all of this was in one apparatus. At the time, it had very high solvent recoveries. And Huber have kept that ethos all the way along with the Huber Ministat, cooling other brands' rotary evaporators, and more recently, development of our CT family, our cold trap family for solvent recovery. In this thermal image here, you can see our rotary evaporator on the right hand side feeding into our CT50. This is the twin model where we've got two cold traps, a primary and a secondary. And in these images here, we can see how our primary side catches the majority of the solvent. Our secondary side catches very little because the primary is that efficient. Why do we need this? We do not want solvents getting into the atmosphere. As mentioned earlier, if you're in a teaching lab environment, you are often using single pass water. So if we were to compare single pass tap water versus a Huber Mini Chiller 300 for reproducibility. And what we did here is, working with the university in Sheffield, we actually went into the laboratory and we carried out some physical testing. So here on this graph, you will see the deviation, the black line, of water-cooled systems, so single pass, and the average solvent recovery where we're using a mini chiller and reproducing our solvent recovery rates. Again, the case of diethyl ether, you'll see as it's quite a volatile solvent, under single pass, you get a wide range of recovery. Okay, you might go, oh, Paddy, that's 84% versus 94%. But if you're in a teaching laboratory, that could equate to 8 to 10 litres of diethyl ether that you're losing to the atmosphere every day. And therefore, not fulfilling your quota of solvent in versus solvent recovery to the solvent manufacturers. So if we dial in a bit closer and we look at low boiling versus high boiling solvents, obviously we've got diethyl ether, we get a higher recovery for the mini chiller cooling the system, the same for acetone, the same for ethyl acetate. Now if we look at toluene, toluene requires a lot of energy to get it to boil across because it boils at about 110 degrees. Anyone that's ever done azeotropic distillations know that you can normally drag water with it. That's how much energy you've got to put in. So actually, in this case of the application, single pass cooling does give you the same recovery rate as a Huber chiller. However, if we then look at water cooled systems versus the mini chiller versus the rotostat versus our new CT50 range of cold traps, we will see in each case water cooled gives the lowest rate of recovery. Okay, I have to be open here. The Rotostat data was run back in the 80s, but we did the same testing on each of the new applications. So if we look at the Solvent Recovery, we do not have a complete list for the Rotostat because ethyl acetate and toluene was not run. But what we can see is through evolution of the Huber products, we now have a winner in the CT50, given the highest rate of recoveries. And these were rerun about 5 times by various people to make sure we were covering the variables. There is more information to come on the CT50 as we hope to launch it very soon, and the twin model of the CT50. So from this webinar, I would hope we've managed to get some key information across to you about your laboratory distillations and how we can improve cost savings based on water usage, solvent recovery, environmental impact by not having these secondary distillations and losing solvent vapor via your vacuum pump. Return of investment based on can we put multiple applications on a single chiller, and optimizing that single chiller to give you the best recovery of solvents and the best processes possible. And further that, we got future proofing. If your laboratory changes what it's working on, we'd hope that our mini chillers have enough of an operational range to cover that span of work. When it comes to cooling applications, Huber have been working on laboratory distillation since 1980 with the Huber Rotostat. It was revolutionary in its time and won many prizes. We have evolved this through mini chiller range of products which can be used on any rotary evaporator, be it Eka, Buki, Heidolf, whatever manufacturer. It's a plug and play solution for improving your process. All the way through to the CT50, which we will be launching shortly. And we'd like to have shown you that whilst our solvent recovery has always been high, we've been improving all the way along with our product development. And there's some very nice products coming through the pipeline to make this solution even greener. If you have any further questions, don't be afraid of contacting me directly via LinkedIn or my work email, whatever works for you, or your local Huber contact. They'll be happy to share information. We have operational videos, how-to videos. We've got a lot of media at our disposal. Thank you. Goodbye.